Swayam Prabha. Digital India. Educated India.
Hello and welcome to another lecture on control systems. So in the last lecture we've started seeing some of these so-called rules behind the root locus, and hopefully I've managed to convince you that you don't really need to commit these to memory. Most of these follow from rather commonsensical understanding of what roots of a polynomial, how they are distributed, and some application of the angle criteria, which basically has its origins in just simple rules of complex arithmetic. So we saw specifically, so to say, 5 so-called rules of sketching a root locus, rough sketch of a root locus. The 5th rule, which we've seen only one part of, I would put it to you, which is when we ask the question that what about these n minus m asymptotes, right? So we saw if there are n finite open loop poles and m finite open loop zeros, then m of the branches terminate at the m finite open loop zeros, but there are still n minus m branches which have started at the open loop poles which have to head towards infinity. We also justified why they head towards infinity. In the last lecture we ended on the note that we saw along which directions they head towards infinity, right? But I told you that we may not be completely satisfied with just that bit of answer. Why? So here's how I would motivate this. Let's take this example. Now suppose you have this system GS given by s plus 2 into s plus 3 divided by s plus 1 into s plus 4 into s plus 5 into s plus 7. Okay, this is G1 of s. And then you have G2 of s given by s minus 2, s minus 3 divided by s plus 1 into s plus 4 into s plus 5 into s plus 7. Notice that the poles are identical in both these cases, but the zeros are exactly reflected about the imaginary axis. So for instance, in this case, you have the zeros, let me put the zeros here, minus 2 and minus 3, right? And you have a pole at minus 1, minus 4, minus 5, and minus 7. So clearly, okay, let me draw both of the pole zero maps and then we'll talk about what is clear. Yeah, here we have the zeros on the right half, 2 and 3, and then you have the same pole distribution, 1, which is a minus 1, minus 4, minus 5, minus 7. Now, clearly, if you want to draw the root locus, you will see that this is part of the root locus, this is part of the root locus, and this is part of the root locus here. Here, this is part of the root locus, judging by that odd number of poles plus zeros to the right. This is part of root locus, this is part of root locus. Alright, yeah. Now you see, in many other factors, these root loci will look different. In fact, the distributions are different because of the locations of the zeros. But in so far as this asymptote is concerned, yeah, this asymptote cares not about the absolute locations of these. The asymptote, up until this point, whatever we've seen of this asymptote, only cares about the difference between the open loop poles and zeros. And in so far as that is concerned, you see the number of open loop poles is 4, the number of open loop zeros is 2. Here also it's 4 and 2. So then what are these angles? 2q plus 1 pi upon n minus m, which is basically 2q plus 1 pi upon 2, where q is equal to 1, 2, okay, did I, yeah. So did I take it from 0 last class? Maybe I took it from 0. If not, then I made a mistake. Yeah, no, it's okay. I've taken from 0. So let me take it from 0 again, because as I said, this keeps repeating. So this goes from all the way from 0, 1. Actually, it will not go to 2, because n minus m is 2. So n minus m minus 1 is, we need only 2 roots. No, there are only 2 asymptotes. So you plug in 0 here, and you get one asymptote is along pi by 2. So your asymptote angles are pi by 2, the other is 3 pi by 2. Now the question is, look, you might naively just say, okay, you've just claimed that there's this big circle to which the absolute location of this puny little roots, puny, I mean the distances from the origin are really not significant compared to that huge circle that we've drawn there. So you might say, well, you just told us that, look, to a big circle, looking at it from the periphery of a large enough circle, these points, the distribution of these points and the distribution of these points matter not. And from an analytical perspective, that's true. So you might as well draw this as an asymptote and this as an asymptote for this system, and you might also similarly say that this system also has the same asymptote. But as control systems engineers, we ought to know better. Yeah? So having right half plane zeros is not the same as not having right half plane zeros. Okay, the behavior changes, and more so in closed loop. We shall see more of that when we go into root locus, more details. But for now, you at least should appreciate that a control systems engineer will never agree that this G1 and G2 should be similar. And yet, insofar as the angles of these asymptotes are concerned and sketching the asymptotes, of course the angles we cannot control because these angles are just dependent on the difference between the number of open loop poles and zeros. But at least the location of these asymptotes, somehow we feel that they should account for the distribution of the poles and zeros. Maybe not an exact location, but this tells me nothing. In the other words, only when I am at the periphery of a large enough circle can I say, yeah, this 90 degree and this 270 degree, these are the asymptotes. And this is a fairly accurate representation of the root locus. But if your radius is not very small, I mean not very large, if you are actually close enough, if you have drawn a circle like this, then this asymptote and this asymptote are very inaccurate. It makes no sense to say that both these root loci should be along the same direction, at the same place. Yeah? Because we know that you cannot satisfy the angle criteria at the same point for both of these kinds of root distribution. So effectively that asymptote is not telling me anything when the value of k is actually not as large as I want it to be. Of course, you might still argue, well, the idea of an asymptote is, look, to eventually figure out where the poles or where the closed loop poles migrate when k is large enough. So why are you bothered with figuring out how these asymptotes behave for smaller values of k? And there is some logic in that. But we would say that, well, we still want to have a better idea of where to start this asymptote from. And it is this motivation that leads us to figuring out that these two systems should have their asymptotes originating or intersecting with the real axis at different points, not both be at the origin. Yeah? Okay. So how do we go about doing that? The way to do that, it turns out, is we say that given any system, whether it's G1 or G2, we want to approximate it by a system such as 1 by s minus alpha to the n minus m. So we also want to approximate this 1 minus alpha 1, and we want to approximate this by s minus alpha 2 to the power n minus m. Why are we saying this? So somehow we want to say that this alpha 1 captures some essence of the pole 0 distribution, the open loop pole 0 distribution of G1, and this alpha 2 captures some essence of the open loop pole 0 distribution of G2. In that sense, you would then see that if we want to draw the asymptote for this, instead of starting the asymptote at the origin, we would actually start the asymptote at alpha 1, and for this system we would start the asymptote at alpha 2. That is our motivation behind trying to figure out where these asymptotes actually intersect the real axis, some approximation. So bear in mind, this is not an accurate depiction. This is still an approximation. We are approximating a fourth order plant here, for instance, with two poles, two zeros. So the relative degree is 2. Remember? So if you have a relative degree R plant, you are approximating it by a plant having R repeated poles at a fixed point on the real axis. Okay? So the entire basis of this approximation is, okay, let me define that term then, relative degree. So relative degree is nothing but n minus m. Okay? So first let me define this relative degree here. Relative degree is equal to degree of denominator minus degree of numerator. In our notation, it's basically n minus m. So the approximation we make in order to get a better asymptote, okay, is the relative degree R plant or transfer function is approximated as a transfer function having R repeated poles at a point on the real axis. And how are we going to do this? Here's how. So again, go for that plant. It's bm s to the m minus 1 plus bm s to the m, bm s to the m plus bm minus 1 s to the m minus 1 plus dot 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 till b0 divided by, so suppose this is your g of s. This is s to the n plus a n minus 1 s to the n minus 1 plus dot 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 till a naught. Yeah, and we are trying to approximate this by 1 over s minus alpha to the n minus m, where the unknown is this alpha. This is what we are trying to evaluate. Remember earlier we had shown you that the asymptote for s to the n minus m will begin at the origin. So now we are just shifting it to alpha. So we are saying that this asymptote, instead of for all relative degree 2 plants, the asymptotes will head along pi by 2 and 3 pi by 2, and instead of saying that for all relative degree 2 plants they will all start from the origin, we will say that okay, we want to capture some essence of the pole 0 distribution, and that is the reason why we want to approximate it in this fashion. Okay, so how does this work? Here's how. So you then look at this, forget about this part for the time being, just look at this. You look at this and you find what? We say that this is 1 over s to the n plus a n minus 1 s to the n minus 1 plus dot 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 till a naught upon bm s to the m minus 1, sorry, again it's bm s to the m plus bm minus 1 s to the m minus 1 plus till b naught. Okay, all right. So let's say we pull out this bm. Actually we could have pulled out this bm outside, it's like a constant factor, no? So let me just pull out this bm here. So then what you'll have is basically monic polynomials, bm, and this is all bm. Yeah, so that is nothing but some bm, call it some constant. Yeah, no, this is basically s to the n plus a to the n minus 1 s to the n minus 1 plus dot 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 plus a naught upon s to the m plus gamma m minus 1 s to the m minus 1 plus dot 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 till gamma naught, where gamma I is equal to bi upon Bm. Okay, so that's just redefining the polynomial. Yeah. Now notice that what is gamma m minus 1 and a n minus 1? Recall that a n minus 1 is equal to minus the sum of open loop poles, right, and gamma m minus 1 is equal to minus the sum of open loop zeros. Why? Recall in a quadratic polynomial, for instance, ax square plus bx plus c. So minus b by a turned out to be the sum of the poles. So in any polynomial, you can always see that if you write a polynomial, again let me do a side bit of calculation here. So if you, for example, write, let's forget about this notation, let me just write it in the form. So s minus a1, s minus z1 into s minus z2 dot 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 till s minus zm. So this will be s to the m, and what is the coefficient of s to the m minus 1? If you carefully collect together all similar terms, you will see that this is nothing but minus z1 minus z2 minus z3 so on till minus zm plus dot dot dot. So basically the coefficient of the second highest degree is basically the sum of the roots of the equation. So by the same token we can say that these two terms, this an minus 1 and this gamma m minus 1, they give you the sum of the open loop poles and the sum of the open loop zeros respectively, of course bearing the negative sign. Now I am going to just carry out this long division. I know it's probably boring and you've not done these sort of divisions and stuff since your middle school days maybe, but I'm just going to carry out this long division. So this is s to the n plus a to the n minus 1, s to the n minus 1 plus dot 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 till a0. Right? So notice that I'm going to first multiply by s to the n minus m. Yeah, and so that gives me s to the n. But when I multiply this with this, what I then get is n minus m plus m minus 1, that is s. So I get gamma m minus 1 s to the n minus 1 plus so on and so forth. I don't really care much about all of these other terms. So if I now take the remainder here, the highest coefficient now is a to the a n minus 1 minus gamma m minus 1 s to the n minus 1 plus so on and so forth. Now what about the second term? If I try to divide again, I have to now take s to the n minus m minus 1 a n minus 1 minus gamma m minus 1 plus dot dot dot. So of course a standing assumption here, and I'm going to justify that assumption. The assumption is that n minus m is greater than 1. So not only is it a strictly proper or a strictly proper transfer function, but it's actually got a relative degree more than 1. Why am I not interested in the case when n minus m is equal to 1? See, go back to another earlier rule that we derived the other day, that odd even rule. Look at this. See, when n minus m is 1, you have exactly one pole, one open loop pole in excess of the number of zeros, right? So if the number of zeros is even, the number of poles is odd. If the number of poles is even, the number of zeros is odd, right? That is what it implies, no? If you have exactly one more pole than 0, then the number of poles and the number of zeros are two consecutive integers, and two consecutive integers means one of them has to be odd, but the other has to be even. So the difference of the two consecutive integers is 1. The sum of two consecutive integers is obviously going to be an odd number. So if you look at a point, for example, this is a classic example of that case, but even so, if you look at a point here, if all the poles and zeros are to the right of a point on the real axis, then will that point be on the root locus in this case? I am saying yes. Why? Because remember, n plus m is the total number of poles plus zeros to the right, and to a point which is to the right of all the poles and zeros. All n poles and m zeros are to the right. And what is n plus m? N and m are consecutive integers, so n plus m is an odd number. So therefore, any point to the right of all the poles and zeros is already a point on the root locus. So therefore, this stretches all the way to infinity. So the claim is that if n minus m is equal to 1, I already know that there needs to be only one asymptote, because n minus m is 1. And that one asymptote already goes along this pi direction. Yeah. So I don't need to find this, or I don't need to answer this question as to where it will intersect with the real axis, unlike in this case, or for example in this case when you had 3 asymptotes. When you have one asymptote, it's always going to head along this real axis. Yeah. So that is why it's a trivial question, which is why this assumption that we are making here, that this n minus m is greater than 1, makes sense. Because if this n minus m is not greater than 1, then the second term wouldn't come in. And we don't need it either, because we've seen that then that question of approximating by this s minus alpha to the n minus m is immaterial. It already has one asymptote, the asymptote is well defined, it is along the pi direction, the angle of pi, along the negative real axis going to infinity. Okay. So the only interesting case is when n minus m is greater than 1. And here's what it has landed us to in, right. So now notice that this is what the quotient is. So I'm not going to evaluate the higher order terms, that's an approximation. So here's what the quotient is. So then I have this GS is equal to some BM divided by the quotient being s to the n minus m plus an minus 1 minus gamma m minus 1 s to the n minus m minus 1 plus dot dot dot, and finally some remainder which will be a rational function. Some remainder will be there at the end, which is a rational function again, no? Yeah. The moment you keep dividing, you will keep dividing till this degree of this remainder here has a lesser degree than m. Yeah, you will keep dividing till that term, and then that last term will be the remainder. So that divided by this divisor is going to give you the remainder. Yeah, it's just straightforward high school or middle school division, algebraic division that we learned. Okay, nothing fancy about it. Now notice that if I am going to approximate this with a transfer function, say something like this. Yeah, I said it's like s minus m, maybe I should have called it bm. Yeah, because after all, as s tends to infinity, the gain is bm. Yeah, okay. So yeah, let's see where this takes us. So this is bm, and then we want to approximate this by s minus alpha to the power n minus m, which if we expand, we will get bm upon s to the n minus s to the n minus 1 alpha, and we have n minus m, yeah, by the binomial series. We are expanding by the binomial series, okay, and then you will have some plus some terms like this. So now we are going to equate the first two terms, okay, we are going to equate the first two terms here. Alright, so what do those first two terms tell us? Let's see. So this is going to be alpha s to the n minus 1. Yeah. So what are the first two terms going to tell us? Let's see here. Here we have gamma m. Yeah. So the first two terms equating will tell us that we have n minus m times alpha. Remember, alpha is what we are trying to evaluate. So you have n minus m times alpha with a minus sign, of course, is given by a n minus 1 minus gamma m minus 1. Yeah. So therefore, we can write alpha is equal to a n minus 1 minus gamma m minus 1 with a minus sign upon n minus m, which is, now recall this expression that we had, a n minus 1 is minus the sum of the open loop poles and gamma m minus 1 is minus the sum of the open loop zeros, right. So this gives us that this is the sum of, if you absorb this minus sign inside, this is the sum of the open loop poles minus the sum of the open loop zeros divided by the number of open loop poles minus the number of open loop zeros. Okay, so this is the so-called centroid, where the asymptotes intersect the real axis, and this only makes sense when this n minus m is not equal to, or this number, this difference is not equal to 1. Yeah, because if it is equal to 1, it really doesn't make any sense. We already know that asymptote goes to infinity along the negative real axis, as we've explained so far, right. So this, then let's quickly take an example now, alright, excuse me. So for example, we have this G1s, let's say is 1 by s plus 1 times s plus 2 times s plus 3. So there are in fact no zeros here and only 3 poles here. So what are my pole maps here? It's at minus 1, at minus 2 and at minus 3. So immediately I know where the root loci are on this axis, and I also know that it's going to be here, right. So obviously there's going to be somewhere that they're going to break away like this. We'll see that shortly, maybe in this lecture or in the next. We'll see those refinements. But for the time being, it suffices for us to find out where the asymptotes are headed and which direction. Which direction is very easy. We already know it's 3. So we've already evaluated this in the previous lecture. You see, when this number is 3, yeah, then this goes to 0, 1 and 2. So you apply 0, 1 and 2 here. If you apply 0, it's pi by 3. If you apply 1 here, it's pi. And if you apply 2 here, it's 5 pi by 3, yeah, which is basically pi plus 2 pi by 3, which is essentially along 300 degrees, right. So we already know these directions. But now that we have attained this value of this centroid, we have obtained this, let's evaluate this centroid. So what is this? This is sum of the open loop poles minus sum of the open loop zeros upon number of open loop poles minus number of open loop zeros. So that is equal to, what are the sum of the open loop poles? Minus 1, minus 2, minus 3, and minus, of course, there's nothing to subtract here, so we just let it be. Yeah, there are no finite open loop zeros. So this divided by 3, because the difference is 3, the relative degree is 3. 3 poles, no zeros. So 3 minus 0 is 3. So this is 3 plus 3, 6. So minus 6 by 3, that's minus 2. Yeah. So essentially, then we find that the asymptotes will intersect at this. Okay. So as k goes to infinity, so we can expect that, I mean, even without much thought, we can say that, you know, at some point here they will break away. Why they will break away, we'll explain that shortly. Because, you know, at this point it's coming from this side as k increases from 0 to infinity, and at this point also it's coming from this side as k increases from 0 to infinity. But at some point here they have a common point. Common point means that at that value of k, the closed loop poles become repeated poles. 2 branches of the root locus, when they intersect, it means 2 or more branches, it means that it leads to repeated poles, and we'll see repeated closed loop poles, and we'll see that this has consequences in our next refinement, the first refinement in fact that we'll see, which is the breakaway and break-in points. So anyway, what I'm saying is essentially that this is how we can expect the root locus for this system to be. For now, you just have a little faith and just believe me when I say that this red is what the root locus of this system is going to be like. Okay? Oh, sorry, I made a mistake, no? This is not going to be along this direction. I actually looked at the other example probably. So the direction is going to be along this. Yeah, it's going to be 60 degrees and 240 degrees. So actually this root locus is going to go along this and along this. Yeah, right, bad mistake. Hopefully I have corrected it. Yeah. So these are going to be the asymptotes. The asymptotes are going to intersect at this point -2, and the actual root locus will go somewhere like this. Okay. So it will have a breakaway point here, which again, as I said, we'll explain shortly. Yeah. So this is R, this is JR. Yeah, that was a bad mistake. I just didn't evaluate the angle. But the angles, as you can understand, will be of the same pattern as this Butterworth pattern which we discussed the other day. Yeah, along this 60 degrees, 180 degrees and 300 degrees. All right. Okay, so we've seen one example of how this actual evaluation of the centroid is important. If I did not evaluate the centroid, I would have blindly just drawn this from here, which of course, as you go to infinity, really this gap between these two, compared to a large circle, the gap between these 2 points is just puny. It's insignificant. But at lower values of k, it turns out that this asymptote gives me a better approximation, a tool to approximate this root locus in a better fashion. Even if I don't sketch this exact root locus, so if I just am happy to draw the approximate root locus like this. So let's say now the blue one is the root locus. So I draw the root locus in this fashion and I just say, okay, this is my approximate root locus. Okay. I of course know that this is not going to be the exact root locus, but this is still good enough. I get the qualitative idea that at some point if I keep increasing my k, the closed loop poles will migrate to the right half plane. So there is a chance for instability, right? That is essentially a very important, a key qualitative understanding, whether I can keep increasing my k, because remember, we are always interested in trying to increase this k to reduce the steady state error. So here also, what that exact value of k is, the bound, has to be evaluated more carefully, but at least I know that I cannot keep on increasing the value of k as high as I like. In contrast, so let me take this other example. Let's say I take G2S is equal to 1 by S plus 3 times S plus 5. So here you will see that that earlier asymptote which I had drawn by mistake will actually be the correct asymptote. So now what is my alpha? Alpha is going to be minus 3 minus 5 upon 2, because number of poles is 2, number of zeros is none. So it's 2 minus 0 is 2. So this is going to be minus 4, right? So let me draw this rough sketch. So this is my pole 0 map, because there are no zeros. So this is minus 3, this is minus 5. And what is the direction of this? So it's 2q plus 1 pi upon 2. So I know that it's pi by 2 and 3 pi by 2. I have already seen that. So q evaluate to 0 and 1 and you'll get this. Yeah. For q is equal to 0, it's pi by 2. For q is equal to 1, it's 3 pi by 2. But the interesting thing is that I've evaluated this. So this allows me to infer that this is how my root, okay, let me use a different color. So this allows me to infer that this is how my root locus is going to look. Look, the root locus is going to exist in this segment of the real axis only. Beyond this, there are 2 poles on the right. So the total number of poles and zeros is even. So no root locus can exist beyond this. No root locus can exist before this, because 0 is counted as an even number. So essentially what then happens is that basically the branches of the root loci, they emerge from minus 3 and minus 5. They come here, they intersect with each other. Rather, they don't intersect, they actually collide with each other sort of. And then they go off in the complex plane as conjugate pairs. Okay, and they go off in this direction. Alright, so this is R, this is JR. So in this case, you notice that I have no fear of the closed loop poles migrating to the right half plane. So in this case, it turns out that I can actually keep increasing k to as high values as I like, without any fear of losing my closed loop stability. Okay, right. So this is an interesting difference, yeah, and you'll immediately observe that this difference is arising out of the relative degree of the plant. Because of the relative degree and the location of the centroid on the strict left half, and here is why it is important. Now note that if I hadn't told you this centroid location, then for a system like this, where the two poles are here and here, right, you would still draw the asymptote from the origin, yeah, and for a system such as this, which is the one I have just drawn here, you would still draw the asymptote like this. So this asymptote, although it tells me the direction of the asymptote as k is very large, it is not really very meaningful in inferring such things as whether at very high values I am losing my stability or not, whether it is crossing over from the left half plane or not, yeah. So these two have identical asymptotes if I did not account for this difference in alpha. So that is why that evaluation of the centroid is critical. Although you might argue that it is some sort of a refinement and an approximation, but it does convey meaningful information. Okay. So now that we've come up this far, maybe we'll have time for describing one of these refinements which I've just spoken about at so much length, which is this breakaway point. Okay. But before we go into the breakaway point, let me just make a claim here, something that you might find a little confusing at some point in time later while handling some examples, but you should never confuse yourself, which is a given branch of a root locus never intersects itself, which is to say that if you have, for example, a root locus, say starting from here and say somewhere here, right. So if you for example, if you try to draw this root locus, you should never have a root locus pattern that looks like this. Okay, I mean, I don't care, the root locus may, for all practical purposes, may look like this, but it will at least never look like this green line. Why? What is so bad about the green line? The green line says that at this point the branch has intersected with itself. And why is that not possible? It's not very surprising. If you think about it a bit, what this is saying is that as I am changing k, so as I am heading away from this, my k is increasing. So when I first went through this point, I came across this at some value of k is equal to k1. And then I again came to this point at some value k is equal to k2. So it's basically telling me that at the same point on the complex plane, I can have k is equal to k1 and k is equal to k2, where k1 is not equal to k2. But how is that possible? Go back, many slides back, maybe I'll just draw it here again. How do we after all evaluate this k? Once you found that a particular point on the complex plane qualifies as a point on the root locus, what we then do is we take all these poles and zeros, alright, we take all these poles and zeros and draw the lengths, right. So we draw these lines from all these poles and zeros to this point on the root locus, and then we say if this is P1, this is P2, this is P3, so we call this LP1, we call this LP2, we call this LP3, and this is LZ1, this is Z1 and this is Z2, we call this LZ2. So at this point, the value of the gain k is uniquely given by what? I know that 1 is equal to magnitude of k times Z1, LZ2 upon LP1, LP2, LP3. So in other words, the magnitude of k is given by LP1, LP2, LP3. If there are more poles and zeros, obviously you see the extension readily. LZ1, LZ2. Now notice that this is unique. So for every point on the complex plane that qualifies as a point on the root locus, the value of gain is unique. So therefore, if a single branch of the root locus intersects itself, it means it contradicts this very uniqueness, no? It just tells you that at this point you can have once when traveling through it for the first time, you had k is equal to k1 and then you kept increasing k, and then you encountered this again. It means that at the same point, yeah, at the same point you have two different values of k, because that is the very definition of a root locus. One is coming from the definition of a root locus, that the locus of all points as k is varied. So therefore k1 and k2 are definitely distinct values. But from the other end, you see that this is a one-to-one correspondence. For any point on the root locus, the value of k is uniquely determined. So therefore you have to have k1 is equal to k2 from this aspect of uniqueness, but from the other aspect k1 and k2 cannot be equal. So in other words, this is a contradiction which tells you that a given branch of the root locus cannot intersect with itself. But here's the next bit. Two different branches of the root locus can collide. Okay, so suppose for example you have, as we've considered in the other case, where you had -3 and -5 and then you had the asymptote emerging from through -4. So this is one branch. Let me color it with branch B1, and this is the red branch which is B2. Okay, so this is branch B1, this is branch B2. So now as you go from branch B1, you are increasing k. So this is at k is equal to 0, then you slightly increase k until you reach this point where you have some k is equal to k dashed. Okay, now remember that at this point there are not two branches that are intersecting, okay, or that are colliding. So therefore there is no contradiction here, because at this point this branch has also emerged from here, and at k is equal to k dashed it sits here, and this branch has emerged from here and at k is equal to k dashed it sits here. So there is no contradiction here, and at exactly k is equal to k dash they start to break off in these two directions. And now you might wonder, okay, which branch is going where? The simple answer is I don't care. Once they have collided, I can easily say that this branch has gone in this direction and this branch has gone in this direction, or I might also say that this branch has gone off and headed in this direction and this branch has gone off and headed in this direction. It really doesn't matter, no? It makes absolutely no difference insofar as this conclusion is concerned, right? So therefore, till the collision of two branches happen, it makes sense to distinguish between them. Once the collision has happened, I don't really care which branch is named as which one. They are indiscernible thereafter. Okay, so remember these two important points. Till a branch of a root locus hasn't collided with another branch, it cannot intersect itself. But once it has indeed intersected or collided with another branch, then you might as well name the branches to emerge. So this is what is called a break-in. So two branches are colliding, coming towards each other, that is a break-in. And once they have broken in, then they break away. Alright. So, of course, we are only talking about break-ins and breakaways that happen on the real axis. So in this case, yeah, whatever happens along the real axis is not counted. So for all practical purposes, this will be called a breakaway point. Ideally speaking, this is both a break-in and a breakaway point, but the break-in happens along the real axis, the breakaway happens, say, perpendicular to the real axis. Okay. On the other hand, suppose for example you had a root locus like this, say 2 zeros here and 2 poles here. You can give these any convenient numbering, alright, and then obviously we know that they have to end at the zeros and they begin. So there is a breakaway that is happening here. So of course the break-in is happening along the real axis, but the breakaway is happening away from the real axis, so we call this a breakaway point. So this is called a breakaway point, and then it comes in and breaks into the real axis here. Of course this is symmetric, even if my sketch doesn't suggest so. So this is a break-in. It's a break-in point. Again you might argue that, well, the two branches are also breaking away to the real zeros, but again whatever happens on the real axis we don't count them, okay. So it might be breaking in along the real axis here and breaking away from the real axis. So whatever happens to it after it leaves the real axis or before it enters the real axis is what defines whether it's a break-in or a breakaway, yeah. Ideally speaking, you might say this is both a break-in and breakaway point, this is also both a break-in and breakaway point because two branches are breaking in and two branches are breaking away at the same point. But the nomenclature is such that if it's breaking away from the real axis, we call it a breakaway point. If it's breaking into the real axis, we call it a break-in point. Yeah, that's it. It's just a nomenclature that you would do well to keep in mind. Now, does that mean, yeah, that there cannot be more than two branches breaking in and breaking away at a particular point? Of course they can. In fact, we will shortly, maybe not, if not in this lecture, we'll shortly take an example in the next lecture, where we shall see that this break away or this break in, they can happen simultaneously at a point, yeah, and where multiple branches, not just two branches, more than two branches can also intersect at a particular point, okay. So enough said about all those general results. How do you obtain this breakaway and break-in point, or is it like really something that is too fine a point and that we cannot do, right? That maybe we cannot evaluate this breakaway and break-in point like we evaluated the centroid. Can we at all evaluate this breakaway and break-in point on the real axis? That is the question. Okay. To answer that question, we observe certain phenomena. See, if a polynomial has repeated roots, say for example it has s minus a squared times s minus b times s minus c, then what is p dashed s? P dashed s is 2 times s minus a times s minus b times s minus c plus s minus a squared times s minus c plus s minus a squared times s minus b. So you notice that you can still pull out this s minus a factor common and something will come in. So basically, if a polynomial has repeated roots of multiplicity r at a point A, then by this extending this you can easily try that out. You can take the second, you can take this s minus a cubed and you can take the second derivative. Then what we are saying is, then okay, let me write it in the same slide. Then we have of course if it's a root, then p of a vanishes. So this polynomial is p of s, let's say. P of a vanishes, p dashed of a vanishes at that point, till you go till the r minus 1th derivative of p at a. So all of them will vanish. So this is an observation, okay, and this will help us in our evaluation of this breakaway and break-in point. What have we just observed? After all, look, a breakaway and break-in is when two branches, at least two branches, if not more, at least two branches come in and collide at a point. What does that mean? That this branch starts at k is equal to 0, comes in here at some k is equal to k dashed. This branch also starts at k is equal to 0 and starts at some k is equal to, and stops at some k is equal to k dashed. We've already seen that at any given point the k value is uniquely determined. For any point on the root locus, the k value is uniquely determined. So if this is a common point for two branches, then if along one branch this gives a value of k in as k is equal to k dashed, along the other branch also this must give a value of k is equal to k dashed. Now what happens at this point? If this root, this branch means it's this one closed loop pole started from this open loop pole and started migrating and reached here. The other closed loop pole branch started at this open loop pole and also came here. So it means at that point there is a repetition of those poles. So if there is a repetition of those poles, can we not write at a break away? I mean, same argument holds for the break in as well. Yeah, two branches have come in together. So at that exact point there is a repetition. So at a breakaway or break in point, we have say the point is A. We have KNA plus DA is equal to 0, alright, and at least we have Kn dashed A plus D dashed A is equal to 0. So this is equation number 1, this is equation number 2. So therefore we can write this as, replacing in the first one, we replace the K term here. So K from the first equation can be written as minus dA by Na minus dA upon Na, of course assuming that this A is not also a root of the numerator, so it's not also an open loop. Suppose not an open loop, 0 itself. So then we write this as N dashed A plus D dashed A is equal to 0, which then lead us to, now we can also divide by dA, so we'll just make the assumption not an open loop 0 or an open loop pole. So we'll say that this is N dashed A upon NA is equal to D dashed A upon dA. Now notice something. After all, what is this ds? There are different ways of writing this denominator polynomial. This ds is something like s minus p1, s minus p2 dot 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 till s minus pn. Even if you are counting, so these are not necessarily all distinct. So p1 and p2 can be the same. So we are just opening it up. If it's s minus p1 squared, we are just writing it as s minus p1 into s minus p1, right? Simple enough. Similarly, we write this ns as equal to s minus z1 dot 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 till s minus zm. Now what is the derivative? If you apply the chain rule of differentiation, you will see that this basically tells us that for every term, how many terms will be there? There will be n terms in the derivative. So in d dash there will be n terms, in n dash there will be m terms. In each term of this, you take the differentiation, one term will drop out. Yeah, it's a chain rule. So it's the product. If you take the product of two functions f and g and you differentiate them with their respect to their argument, which is x, then the product. So basically we are applying this product rule. So if you have f and g and you are taking the ddx of f and g, then you will get f dash g plus f g dashed, right? So same thing, you just apply this to multiple products here. So there are n products and m products here. So this is going to be nothing but, you see, in every term in the numerator, one term is short, but in the numerator, in the denominator side, that is Na, you will have all these terms. So this is always s minus z1. S minus z1 dot 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 till s minus zm is equal to, this is s minus p1 dot 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 till s minus pn, and in the numerator you have, first term you drop s minus z1, so it's s minus z2 dot 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 till s minus zm. Likewise to the last term you drop s minus zm, s minus z1 dot 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 till s minus zm minus 1. Similar thing here as well, you have in the first term you drop s minus p1, so it is s minus p2 onwards till n minus 1 terms, s minus pn, and likewise in the last term you drop s minus pn, so you have s minus p1 dot 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 till s minus pn minus 1. But now if you open up this as a sum of m terms here and n terms on the other side, what happens is then, you see that from the first term, every other term cancels out with the denominator except s minus z1. So therefore this turns out, you can just check it out if you open it up, this is nothing but s minus zi, I is equal to 1 to m, is equal to summation 1 by s minus pj, j going from 1 through n. So that is the condition. This is the equation you have to solve, depending on how difficult or easy it is. This is the equation you have to solve to obtain potential break in and break away points. But notice you are not done. This is just a necessary condition for a point to be a break in or a breakaway point. So obviously this, if you try to solve, this will have nth degree polynomial. it will have in general complex poles, or complex roots, sorry, right? Some of them will be complex, some of them will be real. Not just that, you'll have to find out the solution of this, and then you'll have to check if each of those solution, if each of them satisfies. So this is only a necessary condition for a point to be breakaway or break-in point. But thereafter, you have to check whether that point actually satisfies the angle criteria. Check if the solution so obtained satisfies the angle criteria. Only if it passes through this filter, that it satisfies this equation, it is a root of this equation, and it satisfies the angle criteria, only then you would say, well, yes, this is a potential breakaway or a break-in point. Okay, there's another interpretation of this. So this will in general also give you, so there's no reason to suspect that two branches of the root loci can only collide at the real axis. They can also collide in the complex plane. So for example, you can have a root locus, suppose, that looks something like this. So let's say you have a root locus of this sort of a system, and you can have a root locus that has one real breakaway point, and then it has two more branches coming here, and therefore two more points where whether you call it, now this is where it's difficult to define it as a breakaway or a break-in, because this is both a break-in and a breakaway. So you might have something like this, a root locus that looks something like this. Why am I drawing it like this? Because there are 4 poles and no zeros, so I know that the asymptotes are along these directions. Yeah. So notice that this is also a breakaway or break-in point. This is also, so there are 3 breakaway or break-in points in this case. So there is no reason to suspect that these branches of these root loci, they can only collide on the real axis. They can collide anywhere on the complex plane, provided it is a legitimate point on the root locus. And this equation will therefore give you all such points and more possibly. So because it gives you more points than are potentially those breakaway and break-in points, you have to check each and every solution of this equation. You have to check and verify that it is indeed satisfying this angle criteria. If it doesn't satisfy this angle criteria, even if it satisfies this equation, it's still not a breakaway or a break-in point. Okay, so the beautiful thing about all this is, it also gives you both the complex and the real breakaway and break-in points. As I said, there's no reason to suspect that breakaway points or break-in points or collisions between branches of the root loci, which we are interested in obtaining, only can occur on the real axis. Okay, in the next lecture, we shall see that if the collisions do occur on the real axis, yeah, then there is another interpretation to this breakaway and break-in point, and hence another way of evaluating, although I am not saying that that will make the solution of this equation any simpler. You will still end up with the solving the same type of equation. Okay, it will not make the solution any easier. So whether you use this method or the other method that we will discuss in the next lecture, it really matters not insofar as simplifying this problem is concerned. It will still remain as difficult. Okay. So that, then you might ask, why are we going to study that? Because it's a beautiful interpretation of this breakaway and break-in point when it occurs on the real axis. So we'll see that, and we'll see a couple of more refinements of this root locus. We've already seen 5 basic rules of sketching a root locus. The first refinement is this breakaway break-in point evaluation of the root locus, which we've also hopefully seen. We'll continue to see this for a little longer, and then we will see a couple more refinements, one of them being how to evaluate. So you've already seen in, for instance, in this example, where was that? So we've already seen in one of the examples, yeah, right. So we already seen in this sort of an example that the root locus might tend to migrate to the right half plane, and drawing just a rough asymptote might not be satisfactory to us. So we might want to exactly find out through which point on the imaginary axis it migrates to the right half plane and what is the exact value of k, the critical value of k at that point. Okay, so that is another refinement of the root locus which we will be interested in finding out, right? And finally we will see that, and this is particularly relevant for complex open loop poles and zeros, that when a branch of the root locus approaches an open loop zero that is complex or tends to move away from an open loop pole that is complex, what is the direction along which it moves? Because on the real axis we have already seen which patches of the real axis contain the root locus, and therefore they head only in one direction, either along 0 degree or along pi. But if it's a point on the complex plane, then it can take any of the possible directions along the 360 degrees. Okay, that's called the angle of arrival and departure. So we will also see how to evaluate those in the next lecture. And once we are done with those refinements, we'll see that using some qualitative sketch only, we'll be able to make a lot of inferences about locations of additional poles and zeros thereafter. Okay, so all of that in the next lecture. Until then, take care. Thank you all.